Welcome everyone. My name is Maximilian. I'm working for Eclipse Source, and I would like to talk to you about how to build cloud-based tooling. Let's dive right into the topic. Before I talk more about how to build it, I would like to define what I understand by a tool. Obviously, there is many different definitions, and basically what I describe here is my experience or our company's experience in building those kinds of tools over a decade or more. Those tools that I talk about are from various domains, so from medical to aerospace, transportation, automotive. So obviously all the engineering disciplines like to have those tools, but also finance. And all those domains, of course, have very different use cases and very different ideas of what they do in those tools. But in the end, the features that they would like to have are very, very similar. And this is what I'm trying to describe here with the prototypical tool that I talk about when building tools, cloud-based tools. So all of those tools need kind of a workbench. The idea of that workbench is that you have some kind of window management. So you can have multiple editors that you can arrange. You often have a navigation explorer or something like that on the left-hand side that allows you to explore the current project or whatever the name for that is in the particular tool. It will provide you with menus, status bars, and the like. Furthermore, in many of those tools, you somehow have to enter the data for the tool and also display the data for the tool, and that's often done in forms. Those form-based editors, in many cases, have a tree to give you an idea of the structure, but then they have a form with fields for each of the properties of some particular entry in the data that you have there. Then many of those tools also have diagrams. So entering all the data in forms might be nice, but some of the data is often better visualized in a graphical way. Especially if the data is about links between things. This is just better visualized in a graphical way and also edited in a graphical way. So many of those tools have diagrams. And of course, there's also textual representations. I mean, obviously, if you have source code in your tool, which is also the case many times, but also if you have some other data or configuration that is more text-based. So think about a textual DSL. So you need textual editors. Then in many of those tools, you have an analysis, or you might even call it a simulation component. It takes the data that was entered into the tool and derives some results of that data. It might run a simulation to give you an idea of what the data would do in a real world scenario. So for example, if we're in an automotive tool, this could simulate a crash or simulate losing a certain part and then seeing how the whole system will recover. So this is an analysis component. And then finally, often enough, some other artifacts are derived from the data that you entered into the tool. So this can be source code, documentation, or other textual artifacts. And they are generated from the data that was entered into the tool. By the way, if you have any questions, you can ask questions in the chat at any time. So just go ahead and do that. We will have time after the talk to go into detail about those questions, and I'll try to answer all of them as good as I can. So now that we've defined what this tool that I'm talking about is, why would you even bother creating such a tool? Probably you're not the right crowd to be convinced by that. But people ask that question. So obviously in a cloud-based environment, you have some unique advantages for those tools. Traditionally, many of those tools have been built in a desktop-based environment and still are. But if you're in a cloud-based environment, you have some unique advantages like no client installation. You can just access the tool as well as the data through a web link. So you can send people a link and then they can inspect some artifact in the tool. You have simple client updates. And for some of the tools, it's important they have some quite performance intensive calculations. For example, simulations can be very performance intensive. So it might really make sense to share physical resources as well. So to run the simulation in a cloud-based environment is better than having everyone handing out a machine to everyone that is capable of running those simulations. You get a modern UI look and feel, obviously, with HTML5 rather than any of those desktop toolkits. HTML5 rather than SWT, JavaFX, Qt. That also increases your maintainability probably over time, because who knows what happens to those desktop technologies. You have a long-term evolution path for those, and obviously it's simpler to find people to build those kinds of tools. So given all that, why are people not building cloud-based tools like the one that I described for a long time already? Well, that's because it used to be a lot more difficult than it is today. So probably even 3 or 4 years ago, I would have told customers of ours that they would have to invest tenfold the resources to be able to build the same tool with web-based technologies than what they can build with desktop-based technologies, if you reuse a lot of the frameworks that are already there. So obviously in the Eclipse ecosystem, there's a lot of frameworks to build those kind of tools. And those frameworks have been developed for over a decade, so they work really well. But now we're also there for building cloud-based tools, and there is a couple of key enablers that help us to do that. Foremost, this is Eclipse Thea. I will go into detail about any of those, but now just for an overview, Eclipse Thea is a cloud IDE platform and can be used to build those kind of tools. Eclipse EMF.cloud is a project which is concerned with building web-based modeling tools. The term modeling can be interchangeably used here with web-based configuration or data tools or data-driven tools. People use different terms there. Eclipse GLSP, which is about web-based diagramming, like the diagrams we've seen before, and Eclipse SHE, and of course also Kubernetes for deploying those applications into the cloud. Only given those key enablers, it became much more simpler to build those kind of tools. And in the recent years, there is a real uptake in applying those technologies and in building tools based on those technologies, rather than building them on desktop-based technologies. So what is Eclipse Thea? A little bit more detail about Eclipse Thea. It's a cloud IDE platform. It supports cloud-based, that is web-based, a web browser-based front end, as well as a desktop-based front end. It just uses Electron for that. It is a vendor-neutral community at the Eclipse Foundation, and it is truly open source. There's many companies involved in that endeavor. Ericsson, Google, Red Hat, Typefox, and also Eclipse Source. It is built for extensibility. So it is really built as a platform, and as a platform to be extended by plugins and extensions. And the main features it ships with is an application frame. So you have window management, menus, status bar, and the like. A code editor for many languages. I'll get into detail on how that's being built, but it can support JavaScript, TypeScript, Java, C++, and a couple of more. And a terminal that allows you to run and integrate other development tools that you can otherwise run from your terminal. And the underlying technologies, the major ones are Monaco, which is a component that's also being used by Visual Studio Code to build the code editor, and the language server protocol. Also, for those two, some more details will be in my talk later on. It's built on Node.js and on Electron for the desktop support. Now, in the remainder of my talk, I'm going to present one example product. It's a modeling tool, as I defined earlier. It's a demo tool. and it's a demo tool to model coffee makers. It has a number of features that I'm going to present throughout the remainder of my talk. And each time I'm going to first present the feature and then show you or discuss how that feature was implemented and which technologies were used to implement it. So first of all, I'm going to show shared editing. That's a quite common use case in those kind of tools, so that you have two editors that basically work on the same data. So they both need to be able to update when the other editor changes something. I'm going to show a tree editor with forms. So a form-based editor. I'm going to show a graphical editor, code generation. So I'm going to generate some code from the coffee maker model or configuration that we've created. I'm going to show you how to work with that source code we've just generated. So we're going to launch a test case, and then we're going to set some breakpoints and so on. Then I'm going to show you an editor for a textual DSL. So it's a text editor for a specific textual DSL for that coffee maker. I'm going to show you an analysis component that analyzes a coffee maker model and derives something from that model. Now let's start with the first demo, with the shared editing demo. So for now, what I have here is a console where I can just launch this coffee editor demo. Later on, I'm going to give you a link to that demo as well, where you can just have the entire source code of that architecture blueprint for building such a tool. Let me just restart that for a second. Probably I didn't kill it off properly before when I tried it last time. No. So what that does now, it launches Thea. Thea has a couple of processes that run on a node server, and it will provide me with this front end. So this is everything we see now is basically Thea, vanilla Thea. We have menus up here. We have navigation between the different modes of the tool. So we have an explorer here in this explorer mode, where you can see the different files in a current workspace, which is also a concept that Thea supplies. We have a terminal view down here, and in the void space here, we will have editors. Can open one. So this is a form-based editor, and I can open another editor on that diagram. And Thea also supplies windowing capabilities, so you can, for example, put those two editors side by side. Now for the shared editing part, it's a quite common use case. We see that those two editors have a very different representation of what they show, but still they show some parts that are similar. So for example, we can see that this drink task down here is also visible in the form-based editor here as an activity within a workflow. And when I start editing here in the diagram, so rename that activity to drink coffee, you can see that immediately the editor also updates on the other side. And of course, this also works vice versa. So if I change the name here, it also updates down here. So seems like a simple functionality, but it's not that easy to achieve and quite crucial for those kinds of tools. So how does that work? So why do we even need a model server? This is the component that synchronizes the changes between the two editors. So the idea here is on the right-hand side, we can see this configuration data or model of the coffee maker. It's essentially a graph with a couple of objects that contain some of the properties, like certain parts of the coffee maker. And different editors in the tool, like here, the form-based editor on the left-hand side, will use different parts of the model that they visualize. So maybe the textual editors takes that part, and maybe the graphical editor takes this other part. And all of those editors are now side by side, but of course we want them to basically change exactly the same runtime state. They could do that by just communicating with each other, but this is obviously not a great idea and doesn't scale. So the idea here is to introduce a component, in this case a component from the emf.cloud project called Model Server, to synchronize the editors. What is emf.cloud? It's an Eclipse project with a goal to enable building cloud-based tools or cloud-based modeling tools. It contains a bunch of components for the cloud covering frequent use cases and encapsulating best practices to build those tools. But it also comes with example tools that provide you with an architecture blueprint. The tool that we're just looking at now in the demo is one of those tools. So this coffee editor tool is part of the emf.cloud project. And those architecture blueprints, they demonstrate how to use the EMF Cloud components, but also how to use other already available open source components to build those kinds of tools. And last but not least, emf.cloud is also an incubator for new cloud-based components. So for example, GLSP, which we will come to later on when we look at web-based diagramming, is a component that was incubated within emf.cloud. What are the features of that model server? As I told you earlier, it shares the runtime state of the loaded models or configuration. If you are familiar with Eclipse modeling framework terminology, it's like a shared editing domain. And this shared runtime state is, of course, potentially dirty, meaning that it was not stored to disk yet. Maybe a user can decide later on whether to persist that state or not. The model server has a command-based change interface, so the editors can send commands to the server to change the model, and the editors can subscribe to certain parts of the model with a notification mechanism via sockets. It's a Java-based server that also allows you to reuse existing model implementations if you have any. It's based on a popular REST framework. And there is convenient model access methods in the REST API to create, update, patch, and save models. Supports multiple formats, JSON and XML, and has multiple client APIs for different platforms, Java, JavaScript, TypeScript. Now let's look into the functionality in a little bit more of detail. There is the first step that an editor usually runs is to load a model. The model server is initialized for the workspace folder of Thea, and then you can load or get a model by supplying the URI of a certain resource or file. This file is loaded only once per session, and other editors can connect to the same session. So share the runtime state. Then editors can subscribe to changes for a certain loaded model, and then they will receive all the commands that other editors have run successfully on that model. And of course, the model server supplies an API to change the model. Editors can send a command. We can see that on the right-hand side here. The JSON forms-based form editor sends a command to the model server. The model server can then decide to apply or not to apply that command. If it applies the command, it will send out notifications that this certain command was applied to the model to all other subscribed editors. And those editors can then update their visual representation accordingly. Okay, so that was how shared editing is implemented. Let's move on to the next feature, which is form-based editing. We have already seen the form-based editor. I've opened that up earlier. The form-based editor on the left-hand side, in this case, has a tree structure. And in the tree structure, you can also create things. This is defined by an underlying schema or meta model that allows you to say what you're able to create in there. So I could, for example, create another control unit. And you can just select things in here, and it'll open up the respective form to edit this particular item in the form-based editor. Now, obviously, this form was not just implemented manually. This form-based editing is based, for the tree, it is based on an EMF Cloud tree component that gives you that hierarchical structure. And for the form, it is based on a framework called JSON Forms, which allows you to declaratively define forms. Those forms are derived from a JSON schema that describes the data for a particular form. So, for example, what we've seen earlier, a control unit has a schema that describes that a control unit has, let's go back to the demo, a vendor, a socket connector type, which is of type enum, a clock speed, which seems to be a number, and so on. And JSON Forms takes into consideration a UI schema, which describes how those different properties are mapped into a form-based UI. So for our example, it would tell us that we have a group that is called processor, and in that group, there is a control for a vendor in a 2-column layout, and it vendor binds to the vendor from the data model, and then underneath there's clock speed and so on. So it gives you a declarative definition, and it renders that, in this case, with a React-based renderer. The form-based editor is then integrated with the emf.cloud model server using its TypeScript-based model server client API, so that the editor can subscribe to, first load the model and subscribe to changes of the model, and also issue commands whenever you type something into one of the controls. Now, the next feature is graphical modeling. For graphical modeling, we've also seen a little bit already. Let's switch back to the demo and bring up the graphical editor. So this is the graphical editor. It allows the things that you would probably expect from it. So it allows you to zoom in and out, and it allows you to create new nodes. So I can just create a new node here. You can edit nodes. In this case, there's only one property within a node. And you can, of course, also connect nodes. So I can make a connection between the two of them here. And that's basically already it. How's that implemented? So in the involved components for that is what I mentioned earlier, the Graphical Language Server Protocol, or a platform, or GLSP for short. The idea of GLSP is LSP for graphical editors. The language server protocol, I will explain a little bit later in more detail, but the general idea is that you have a client, in this case a GLSP client, which is generic. So it is not specific to a certain DSL. It is generic in the sense that it understands that it can draw some boxes and lines in between those boxes, but it doesn't understand what those boxes represent. So it doesn't understand the underlying model that tells you, okay, those are tasks, and there's manual tasks and automatic tasks, and tasks can have flows that connect tasks. It doesn't know that. It only knows there's edges and nodes, and that's basically it. And the GLSP client is responsible for rendering a graphical visualization for that. So the great thing about the GLSP client is then you can just use it for any DSL. It doesn't need to be, it is completely agnostic of the type of DSL. Like an LSP client is completely agnostic about a certain programming language. The GLSP server, however, is the counterpart, and it's the part that the GLSP client talks to. And this is specific to a DSL. Basically, the idea of the GLSP server is it maps a certain model, so a very specific DSL, in our case, a coffee maker DSL, to a graphical visualization. So for example, it contains information that in the context of a coffee maker model, you need to draw a box for every task that is in this model. And you need to draw a line from one box to another box if those tasks have a connection via an edge. And the GLSP server is also the part in this architecture that synchronizes with the model server. So the GLSP server loads the model, subscribes to the respective parts of the model that are visualized in the graphical diagramming representation, and it sends commands to the model server in case something is manipulated. All of that is based on Eclipse Proti, which is a framework that's concerned with diagramming in the web. If we look at that from a component perspective, this is an overview already of how Thea is of a deployment of Thea in the browser. If you have a browser-based deployment, you have the Thea front end running, and the Thea front end can be extended with Thea front end extensions. And in the backend, you have a Node.js server that runs the Thea backend, which can be extended with Thea backend extensions. The GLSP editor is such a front end extension. It plugs into the Thea front end. It basically tells the front end that whenever you open a certain file extension, this editor is to be launched. And as I mentioned earlier, the GLSP editor is an off-the-shelf component. That's why it's in green here. And the yellow, surrounding is basically only representing the fact that you need this little bit of code which registers this editor with the Thea front end and tells the Thea front end which file extension it is responsible for. Now, when you open up an editor, the GLSP editor will connect to a backend extension of Thea. This is the GLSP connector. And the GLSP connector is responsible for launching a GLSP server whenever such a file is opened, and to tell the GLSP server which file it needs to open. And the GLSP server is now a custom component. It relies on the GLSP core, but essentially it's custom implemented. It runs in its own JVM in this case. And the GLSP server connects via REST API and sockets to the model server to subscribe for updates, load the model, and send commands so that other editors can also synchronize on the same state. Now to the next feature, generators. So for many of those models, it makes sense to derive some additional values by generating. Usually this is a model to text generation. So you take the model as an input and you generate some output from that. In the example we have here, I can generate some code, if I remember correctly, from this form-based editor. And I just select this action here, generate workflow code. And I get a bunch of code dropped in here. So some abstract classes and some classes, essentially a class for every one of those tasks that we had in here before. And there also seems to be a test case that will run a couple of tests on those tasks. The involved components for that generator is another Eclipse framework called Eclipse Extend. With Eclipse Extend, you can quite simply write those kind of generators. And the generator itself was then just bundled into a jar with Maven. And the integration is super simple in this case. We just have registered a command or a menu entry on this context menu. And we just launch this jar via the command line interface and provide it with a parameter where to generate the code to, which is just the selected Thea workspace folder. And it runs and generates that. The next feature, which is kind of logical now, is working with the generated source code. So if we look at the editors that I've already opened up while browsing this is a full code editor. It supports syntax highlighting, as you can see. And it also supports a couple of more features. So if we look at the drink activity that we had looked at previously, there's a pre-execute method in here, and I can just start writing some code. You can see that there's auto completions now. So I will do the classical system out println. And welcome to KubeCon. And there's some more capabilities in there here, which you would expect from an IDE. So if you select a string, you can extract that to a constant, for example. And the code editor will run that refactoring. Now, the next thing I'd like to do is run the test case, because obviously once you've created some code, you would also like to run the code. This is a test case, and I can just start debugging that, which reminds me that while debugging it, it would be great to have a breakpoint. Here's an old breakpoint that I would like to get rid of. I'll set a breakpoint on the line that I've just added earlier here. And then I'll run my test case. And I already hit the breakpoint here. You can see that it's a little bit small because I have a high zoom level, but you can see the call stack here. So I can see where I come from the runner here. The runner just runs everything, including the drink activity, and it's pre-execute. And you can also see that there's local variables. So if we go back here, there's a finished local variable, it seems, and you can see the breakpoints that I have set. So it's a fully functional debug environment, and you can, of course, do other things like step over. Now we can see that we have our textual output that we've created, or just let it continue run. And the test case will eventually complete. Now that was a lot of functionality, but actually that's super simple to do. I would just like to take the opportunity to take a small excursions into the language server protocol, in case you're not familiar with that. The idea of that is a separation of concerns between the tooling for editing code and the actual code or textual DSL and the actual language smarts like autocompletion, refactoring, and so on. Because the tool to edit the code can always be the same. The language smarts obviously are super language dependent. So what you can autocomplete in Java is super different from what you can autocomplete in TypeScript, and what you can do in terms of refactoring also is. The advantages of that approach is that an LSP client is language agnostic. So the editor that we have just seen where we edited Java code is exactly the same editor that you can use to edit JavaScript or TypeScript code or the code of any other language that supplies you with an LSP server. The LSP server, on the other hand, is tool agnostic. It doesn't know which tool it will run in, but it contains all the language smarts. And that's a really great approach, because thereby you can build a tool for any kind of language as long as the language supplies a server which speaks LSP. How did we build that demo for working with source code in this tool? The enablers is the language server protocol, as we've just seen. Of course, there's another important enabler, the debug adapter protocol, which is kind of the same thing as LSP, just for debugging. And we have seen the Thea code editor. The Thea code editor is built on Monaco, which is also used by Visual Studio Code. And it is an LSP client. So it's an editor that speaks via LSP with a language server. And we have seen the Thea debug extension. It uses a debug adapter protocol to support language debug. And if we look at that from a component view, again, like before, we have Thea front end and back end. In the Thea front end, we have the LSP editor, which is just an out-of-the-box component because it's generic. In the back end, we have an LSP connector, also generic. And then we have this LSP connector, in this case for Java, will launch a Java LSP server. In this case, it will launch JDT LS, which is a language server that reuses JDT, the Java development tools of Eclipse. So this is a Java development environment that is run within Eclipse, but in this case it's run headless, and it supports the LSP protocol to be able to serve the editor here. Debug is the same thing. We have the debug UI, a debug connector in the backend of Thea on the Node server, and this connects to a Java debug server that runs in a JVM. All of those components out of the box. So there's not really anything to do if you want to integrate that other than adding the right dependencies. And of course, the Java debug server in some sense then launches another JVM that actually runs your Java program like we just did with the test case. Further on, next feature is textual modeling. That's very similar to source code editing, as we will just see in a minute. Let's just look at the functionality first. So for the textual editing, I have a file here, which is a configuration file. This is a configuration file that we will also use later on to run an analysis. It assigns some values to which probability is considered low, medium, and high. This is based on a DSL, so this has a grammar in the background, and this grammar gives you some validations already out of the box. For example, probability must be between 0 and 1. Otherwise, it doesn't make sense. And in this DSL, you can also make some assertions which of the tasks need to be run with before another task. And this gives you auto completions as well. So this gives you all the existing tasks that are there, tells you what the syntax is. So I need this arrow here, and then you can supply just another activity. So this is also something very common, that you need a textual DSL for some parts of your tool. And how that's being implemented is with a component called xtext. The idea here is that in the front end, you have, again, the LSP editor, just unchanged. And so this is exactly the same editor that you just edited Java code with. You now edit this configuration file. And why you can do that? Because there's an LSP connector that in this case connects to an xtext enabled LSP server. This xtext based LSP server is basically out of the box. We just generated that, but it has a custom component that provides the xtext LSP server with the auto completions of the available tasks. So it's a quite small class that you need to implement. And this connects to the model server to query it for what are the tasks that are currently in the model server. The text editing is the Thea editor. As we discussed before, the LSP server is an xtext LSP server. For this particular grammar, it can be generated. So the xtext framework comes with tooling to generate an xtext enabled LSP server for any DSL you create with xtext, which is really great. And the integration is done with in this case, with the client API that is Java based into the model server. Model analysis. So this is the final feature that I would like to demonstrate. This is to derive some value from the analysis. I already told you that this file is about configuring the analysis, and I'll just run the analysis once. This is a D3-based visualization, and it shows what the potential execution paths are in, maybe I should show that again, based on the activities we have here. So if you look at that, the first execution card has to be push, then it has to be check water, and then it can be either water okay or refill water, and so on. So in this case, the analysis is really simple, but you see where I'm going to. Now, where's my analysis here? So as you can see here, you can just follow that with the mouse now. Now we're at check water, and that can either be refill 50% of the executions or water okay in the other 50%, and then we go on with check deep tray, heat, and so on. How was that realized? So the visualization is done with D3, which is a really great visualization library in JavaScript. The analysis was written with Kotlin because a colleague of mine just wanted to try that once. And the integration is done with the Java-based model server client API. Basically, the analysis component only pulls the current state of the model, which is all the tasks and how they're connected, and creates a D3 visualization out of that. So super simple. Before I do my conclusion, I want to look at one quite frequent scenario, at least for our customers. It's that people don't start from scratch for creating a web-based or cloud-based tool. They already have an existing legacy desktop-based tool. And one very important point that I took from all the projects that I've seen so far in migrating those kind of tools is a very big mistake that you can take is just build the new tool from scratch with a separated team and just hope that at some point it will reach feature parity with your desktop-based tool. There's a lot of danger that you will never reach that point because you don't have enough resources, because the desktop-based tool will get some feature enhancements, and then you have to have those in the web-based tools as well, and so on. So what I would really recommend is to define an iterative strategy, which means that you have a strategy where you can iteratively move to a web-based solution component by component. And that sounds very difficult, and of course it is at some points, but there's also some quite simple recipes. So just to name one, if you build a new feature into your desktop-based application, maybe you can just build it in a web-based way and retrofit it into your existing desktop-based tool by using a browser widget. So in Eclipse, that's quite simple. If you have an Eclipse-based tool, you can use the browser widget there and integrate a browser or web-based component into your desktop-based tool that is then almost 100% identical for your web-based version of the tool. Short term, it is really good to, if you want to migrate to, even if you want to do that in the future, it's good if you already have that strategy so you can consider it for architectural decisions. Like I just mentioned, take the architectural decisions that new components are to be web-based so that you don't have the additional effort later on to migrate them. Midterm, you will prepare your architecture for migration, even proactively. So that means that maybe you replace some of the components, you decouple the components, that you get headless services that run some of the things so that you can reuse them later on in a web-based scenario. You will start to migrate high-value use cases. That's also something I see quite often, that while migrating the entire tool seems not very feasible, it is feasible to migrate high-value use cases, a review use case, for example. And often those use cases have less features than the entire tool. So maybe a review use case can be read-only. It just allows you to make some annotations or notes on the model. And as far as you can, single source components so that you don't have to maintain the source code for the same component in a desktop and a web-based version, so that you have a very high overlap there. Long term, at some point, you will start to migrate use case by use case and then finally deprecate the desktop-based solution. So in summary, what we've seen is components from emf.cloud and an example product from emf.cloud, the Coffee Editor. It's available on GitHub. I'll post the slides with the links. We've also seen that building web-based tools is not that magical anymore today, even for those more complex modeling or configuration tools with the features that I've demonstrated. And they allow you to reuse and migrate if you have a good strategy there. There's also a live demo of the Coffee Editor available, so of the tool that I've shown here. So if you don't want to go to GitHub and build it or run it yourself, you can just go to that live instance. It's hosted on a Kubernetes cluster, and you can just spin up an instance by going to that URL. And if you would like to get some more information, there's a webpage for emf.cloud. If you are thinking about migrating such a tool, then I urge you to really define a strategy and a time plan as soon as possible and build a proof of concept. And with that, I would like to go over to the Q&A session. So let me see. There's one question from Andreas. He is asking whether he can generate from a series-based DSL a GLSP server similar to textual DSLs that are using an Xtext LSP generator. For a series-based DSL, no, I know for a fact. They're using an entirely different set of technologies that's specific to series. I know that they have a web-based version of series now. I'm not exactly sure about the state because it was just released at the EclipseCon about a month ago. So yeah, I don't know how you could do that at this particular point. And they're not using GLSP to implement series diagramming. So that's quite far away. Are there any other questions? If there are, please post into the chat now. If you have some questions later, by the way, feel free to just contact me via email, which I hopefully have on my slides on the first slide deck. If I don't, then I will edit later on. Thank you for your feedback. If there's no more questions, if you're still typing in a very long question, then say something now. Otherwise, I will just wrap the session. Thank you very much for joining and enjoy the remainder of the conference.
Thank you, everyone, again. And yeah, we're going to end it now. And if you want to review the recording, it'll be on YouTube probably later this week. Enjoy the rest of the conference.
Awesome.
Bye.
Thank you very much for helping.